So the second half of 8.1 will still be the idea of going back and forth between these two systems, polar and rectangular, except we're going to be looking at equations rather than individual points. So as you can read, our lesson goal is to represent one equations. It's going to be the same equation, but in two different formats, polar and rectangular form. Now, this lesson will be relatively short because it's not complicated conceptually. We took care of all the concepts yesterday. This subsection, if you will be 100% skill. It's one of those you either are able to do it or you don't know how to do it. It's nothing hard to figure out. It's just all algebra. And of course, as always, the only way you can get better at algebra is with a lot of practice. But let's I want to leave you with some hints, with some foundations and groundwork. And that groundwork, in order to do this, to convert to and from polar and rectangular equations, all stems from the bridges, the algebraic bridges that we created yesterday. So recall from yesterday that we have a series or a set of equations that sort of connect polar and rectangular form. And they were that the x-coordinates to any point is equal to a radius times cosine of an angle. The y-coordinate is equal to the radius times the sine of the angle. On the other side of the coin, the relationship that connects the radius with x and y's is Pythagoras' theorem. R squared equals x squared plus y squared. And how it connects to the angle is through tangent. Specifically, tangent is y over x. And it's through these relationships or these bridges that allow us to go to and from the various forms. Now, I did say that there's nothing new to learn conceptually. This is it. This is the big buildup that we made yesterday. But I do have some tips and suggestions. For converting equations. And let's separate these into two categories. So let's see. Let's start with into polar. So let's see. Tips to go from rectangular to polar. These, in my opinion, are the easiest types of problems or types of conversions because they're the bridges, the formulas. They do all the work for you. We already have direct links that connect explicitly, directly, the x and y coordinates to polar form. So there's nothing really hard to do here. You simply substitute the r cosine theta for every x, substitute an r sine theta for every y, and you want to solve for r or solve for theta whenever possible. I say whenever possible because sometimes the equations might get too complicated and then you can just go ahead and leave it like regular. In other words, you want r equals stuff, or sometimes there aren't any r's, you can just go theta equals stuff. That's what you want. In the other direction is a little bit harder. So if you're going from polar to rectangular, the idea is you want to use algebra to get r cosine theta, r sine theta, r squared, and sometimes, not often, this is very rare, but you want tan theta in your equation. The reason why you want these expressions in your equations is because there are a direct substitution. Because every single r cosine you can change to an x. Every single r sine you're going to change to a y. Every single r squared you're going to change into x squared plus y squared. And every single tangent you're going to change into y over x, which of course is rectangular form. Now you can use anything You can manipulate the equation however you want. You can do anything you want as long as it's mathematically legal. And just like with a polar form, if possible, solve for y. In other words, you want y equals stuff. We typically like to write equations or functions in terms of x's. Now, sometimes that won't be possible because the equation looks too funky, and if the equation looks too funky, just leave it as is, and I'll do a few examples of that. But try, if possible, to write y as a function of x. So again, there really is nothing new to teach in terms of concept. You just got to dive into the examples and practice. But I do want to leave you with a handful of examples just so you get the feel or the idea of it. So suppose I asked you to express the equation. This is what the instructions will say. This is how it's going to be phrased. Express the equation x squared equals 4y in polar coordinates. As you can tell, they give you an equation with x's and y's, so it's so that's rectangular. So obviously they want you to convert it into polar. So to do this, it's very easy. It's just straight up substitution. So this is the easy route. Converting into polar is easy. Just plug in the bridges. Substitute r cosine wherever you see x, and substitute r sine wherever you see a y. So to do this, I see an x, so that's r cosine, equals 4. I see a y, so that's r sine. Easy peasy. So that's r squared cosine squared equals 4r sine theta. Right. Next, you want to solve for r, if possible. Now, notice we have an r squared and an r here. So we have two separate terms of r, but the key thing to note here is we don't have any extra loose terms. There's no plus or minus extra terms here. There's no plus or minus extra terms here. It's just one term equaling another term. So one way you can isolate the r is just to divide both sides by r, right? We have an extra factor of r. Let's get rid of it. But since I also want to get r by itself, I'm going to go ahead and just divide out this extra cosine squared as well. I'm going to do two steps at once. So at this point, I'm going to divide both sides by r cosine squared because I know dividing out the r will get rid of one of the extra factors of r, and I'm going to also divide out the cosine squared to get the r by itself. That leaves us with a single r on the left-hand side, which is exactly what we want, and we're left with a 4 sine theta over cosine squared theta. Because of these r's, they cancel out. Now, technically that's it. We're done. Whoop-de-doo. This is a polar equation. We have r equals. I think the textbook, they don't like to leave it as a rational function. So what they did was they got rid of the denominator by combining the sine and cosine into a tangent, and you had a leftover cosine in the... Well, I'll go ahead and show my work. So what they did was they took one of the cosines and attached it to the sines. And of course, that left you with an extra cosine in the denominator. And then they went ahead and rewrote it without fractions. So that's sine over cosine is tangent, and 1 over cosine is secant. So this, I believe, would be the answer that they provided in the back of the book, in the answer key. Is this a wrong answer? Technically, no. If you put it on the quiz and test, will I give you credit? Possibly, yeah, I probably would. But I have to admit, without fractions, this does look a lot nicer. So just know that when you're practicing on your own, if you get this far and you check your answer and you see this, you should have the mathematical knowledge to know that they're both equivalent. So you can see that converting into polar isn't that hard. Literally, wherever you see an x, change it into an r cosine. Wherever you see a y, change it to an r sine. That's all you have to do. Going the other direction is a little bit tricky. Well, not tricky, but it requires some thinking. You can't just be a mindless robot when you convert it into rectangular. So let's suppose I ask you to convert the following equations into rectangular coordinates. So the first one, suppose I asked you to convert r equals 5 secant of theta. Now remember, your goal is to connect. Sorry, let me just go ahead. It's important enough that I'll rewrite it. So the idea is you want to create r cosines, r sines, r squares, and tangent thetas. So you shouldn't have an r by itself. Every single r you want to attach either sine or cosine to it, or you can have an r that's squared by itself. And if you have trig functions, the only trig function that's okay to be by itself is tangent, because we can convert there. So if I have this equation, the first thing I want to do is I want to convert everything to sines and cosines. So I know that this is equivalent to r equals 5 over cosine theta. Now I have a couple of quote problems. This r is by itself, which I don't like, and this cosine is by itself, which I don't like. Remember, we want to attach the r's with the cosines, attach an r's with the sines, or square the r's, or create a tangent somehow. Well, I chose this example because it's super duper easy. I hope everyone can see that it's super easy to mathematically connect this r with this cosine, right? Just multiply both sides by cosine. So if you multiply both sides by cosines, we get r cosine of theta equals 5. And then, of course, we have this bridge here. We know that r cosine of theta is simply x. And that's rectangular. All the r's are gone, all the thetas are gone. Now, typically you want to solve for y, but since we don't have any y's, this is a perfect valid equation. We're not going to graph this. We're going to graph it tomorrow, but it's sort of an interesting idea that if you were to graph this equation in polar form, it should look like this equation in rectangular form, and we know that x equals 5 is a vertical line. So, it's sort of a neat trivia fact that this equation is a vertical line, a straight up and down vertical line in polar form. That's pretty neat. Let's take a look at an example that's more involved. Suppose I ask you to solve for r, convert r equals to sine theta. Now remember, our goal is to connect the r's and the sines and cosines together, but here's the problem. Mathematically, there's nothing I can do to take this sine and attach it to this r, because some people might go, oh, just divide it over. Well, if I divided it over, I'll have the sine in the denominator, and I do not want r divided by sine theta. I want r times sine theta. So I want this sine here to have an r multiplied to it. Well, I can do anything I want mathematically as long as I balance both sides. So if I want that sine to have a times r, we'll just multiply it by r, times it by r. So we can multiply this guy by r. But of course, what you do to one side, you have to do to the other side. And then we have r squared equals 2r sine theta. And lo and behold, we have exactly what we want. We have r squared, which is a special bridge. We have a substitution for him. And then we have r sine theta, which we can then substitute as well. So we should know that r squared is x squared plus y squared. And then r sine theta is y. Note that this is the beginning of an equation of a circle, because we have both x squares and y squares. So what we're going to do is write it in the standard form of a circle, which means you bring all the x's together, all the y's together, and then you're going to complete the square. So the next thing we're going to do is we're going to subtract the 2y over. I'm going to leave a gap here. The x squared doesn't have any extra terms, so I'm going to leave them alone, but I need to complete the square for the y, so let's refresh our memory. Completing the square is adding just the right amount of constants to make a perfect square trinomial, and that perfect right amount is always going to be half of this number squared. So half of 2 is 1, 1 squared is 1. I'm going to add 1 to both sides. So the act of adding a 1 is what we call completing the square. The reason why you do that is then this trinomial here is now factorable. It's a perfect square trinomial. So if you were to factorize it properly, you would figure out that it would be y minus 1 quantity squared. So that is the equation of the circle. It turns out that r equals 2 sine theta is simply a circle. Let's do one last example. R equals 2 plus 2 cosine theta. So we have lots of going on here. We have multiple terms. We have this cosine that doesn't have an r attached to it. We have this r that's just by himself, that doesn't have a trig function, and there's no way I can mathematically connect this cosine with this r. So we're going to use the same trick as above. We're going to multiply both sides by r because I know I need to have this cosine. I need to have an r attached to him. Well, here's the problem. If I multiply both sides, and I must do both sides by r, it's going to give this 2 an extra r factor. This is, let's just see it here. So the r squared on the left, well, that's easy to handle. That's x squared plus y squared. But 2 times r is nothing. It's not a special substitution, so I got to keep writing it as 2r. And of course, our cosine is simply x. So here's our problem. I'm still not in rectangular form because we have some polar parts. Remember, r's and thetas are polar parts. So how do I get rid of them? Well, the first thing I'm going to do is sort of isolate the r term. So let's subtract the 2x over. So you have x squared plus y squared minus 2x equals 2r. So that just sort of isolates the r. It's sort of like putting it in quarantine. I guess that's, relevant to current events. Now, I know that the only conversions I have that will transform an r into rectangular form is if I attach a sine or cosine to it, or if I square it. Now, attaching a sine and cosine will be difficult because it requires multiplication, and I do not want to put extra sines and cosines on the left. So we need to somehow put a square on him. I could do that by simply squaring the right-hand side, but of course, what you do to one side, you must do to the other. So then we end up with x squared plus y squared minus 2x squared equals 4r squared. And then, of course, the r squared, we can go ahead and substitute x squared plus y squared. Now, you can see why polar form is sometimes helpful. Take a look at the original equation in polar form, compare that to the rectangular equation, which is super duper messy. Now, as always, we always want to try to solve for y whenever possible, but you know what? This expanded is ugly. You got some squares, you got some fourth powers, you got some regular. This is just too gosh darn messy. I'm just going to go ahead and accept this as the final result. Okay. So sometimes if the problem looks too messy, you can just leave it as is. Just go ahead and refer to the answer key to double check your answer. If it doesn't match, that means you have a little bit more extra tweaking and working to do. If it's really big, long, and messy, more likely than not, they just left it as is. So that's it. That is converting to and from polar equation and rectangular equation. It's not hard conceptually. It's just being good with algebra. And the only way you can be good with algebra is if you practice. So have at it. Good luck. And as always, ask questions if you need it.